Hey everyone, this is another thermo question, and before I give you the answers, I highly suggest you try them because personally I found it to be quite difficult initially. Okay, let's get started. I'm going to resize this a little bit so it's a tiny bit smaller. No, I'll just make it bigger, it doesn't matter. Two adiabatics, one isovolumetric and an isobaric process making up the loop ABCDA for an ideal gas. So let's first begin with labeling the legs. By the legs, I mean these individual curves. So two adiabatics, we can see that this is an adiabatic. Same for this one. And this would be isobaric because pressure is the same from A to B. So this is isovolumetric because from C to D, volume remains the same. Okay, now let's try to solve for A. A asks us to determine along which legs, which curve, energy is supplied to the gas or removed from the gas. Okay, let's first inspect leg A to B. No, this is like a vector notation. I don't want to do that. Okay, so to find from the second law of thermodynamics, we know that Q is, aka heat transferred, is change in internal energy plus work done. For this, right now we don't really have to calculate anything numerically, but we just have to know what the signs are. So whether Q is negative or positive to determine if energy is supplied or removed from the gas. Okay, so for A to B, we can tell that the internal energy has increased. So change in internal energy is bigger than 0. Why? Because remember, this is an ideal gas, so the rule of PV equals nRT follows. And we can write this as T is PV divided by nR. And we can see that from A to B, P has remained the same, but V has increased. So P remains the same, V has increased. Everything else remains the same, which means that T has also increased. And when T increases, temperature increases, that means internal energy has increased. And for W, work done, we can also tell that this is positive because you can see that there is an expansion. Pressure remains the same, volume increases. This whole thing is a work done. And because the arrow is going this way, we can tell that this is work done by the gas, not work done to the gas. So work done is positive, which means that Q is positive, which means that heat is supplied. Now, let's check for B to C. So this is an adiabatic expansion. And we know that a characteristic of an adiabatic expansion is that there's no heat transfer. So Q is 0. So for B to C, heat is not supplied and also not removed. And for C to D, this would be in the isovolumetric change. Again, let's set this up as Q is change in internal energy plus work. We can tell that the work done for C to D is 0 because there is no area under the curve. This is just a line, and we know that a line doesn't have an area. Now, for internal energy, we can tell that internal energy here would actually decrease. Now, why is this? Again, let's use PV and R is T. So volume remains the same, but pressure has decreased. Remember, everything else remains the same. If pressure has decreased and it's in the numerator, that means the temperature of the gas has also decreased. And when temperature of the gas decreases, that means that the internal energy has decreased. So 0 plus negative number is negative number. So Q is smaller than 0, which means that heat is removed. Okay, now let's try to do B. Find the relationship between Q in and Q out and net work done in the loop. Honestly, I think it's better if you just guys know this and take this in as a fact. Q in minus Q out. Well, when technically speaking, these are all absolute values. So Q out would be positive. So we're subtracting positive from positive. Is net work done. This is a very useful formula. And I don't think surprisingly, I don't think it's written in the formula booklet. So you'll just have to know this as a fact. Okay, that's it.